SwayamPrabha. Digital India. Educated India.
Hello, welcome to lecture 19, which will be an extension of bidirectional bending of beams as we have been discussing in this week. So, we will also solve another example here to get the theory that we had studied till now much more understand the theory in a much better way. So, the figure that is drawn is the black line denotes the cross section of a beam. So, the cross section of the beam are two semicircles, each of radius r, and these two semicircles are placed symmetrically about the x axis. So, the entire depth of the beam is therefore 4r. So, the problem statement says that you have to find out the maximum normal stress in the beam cross section due to a moment mx equals to 3500 Newton meter. The radius r is 5 mm and the thickness is 0.064 mm. So, I would like to mention that this is a cross section of the beam. So, if we take any beam, the lengthwise axis is z, then the cross section, that is the cross section in the xy plane, is given by the black line. This is a thin wall structure as the thickness t, which is much small compared to the radius of the semicircular cross section. So, now we have solved similar problems in the last lectures. So, this has to be solved in similar lines. But before we solve it, we have to identify certain aspects of the problem and solve it accordingly to minimize the calculation that we will be doing. So, we know, so this is cross section of the beam. So, we know from our previous lecture that the expression for sigma z is given as So, this expression we have been using, we have derived this expression and we have been using it considerably in this week. So, now let us investigate this expression and let us see what will this expression simplify to in for this particular problem. Now, in this problem the cross section has an axis of symmetry, that is the x axis. Therefore, we can say that I x y is equal to 0 for this cross section, which is due to symmetry about So, we all know that the product moment of inertia I x y is always going to be 0 for a cross section which have at least one axis of symmetry. So, it can be singly symmetric or doubly symmetric. It can have two axes of symmetry like a rectangular cross section. thin wall rectangular cross section or a square cross section. So, in that case Ixy has to be equal to 0. So, if we substitute Ixy equal to 0 in the cross section, additionally we have to notice that only mx is non-zero. We have to notice that mx is just given to be 3500 Newton meter and my is equal to 0. So, therefore, sigma z is going to be mx by Ixx into y. So, this is the simplified expression that we have for this particular example. How did we get this? We get this by saying that Ixy is equal to 0. And my is equal to 0. So, this will actually lead to this simplified equation. Now, by looking at this equation, we will see that we do not even need to find out Iyy. So, the only sectional property that we need to find out is Ixx. So, this makes our calculation much more simpler. So, from this expression, we know that find Ixx only. We do not need to find Iyy. So, this investigation should be done beforehand to save the time required to calculate the sectional property. So, we all have realized that the sectional properties are a bit tedious to derive, it is a lengthy process. So, this simplification or understanding of the problem is very important to simplify the problem. So, let us now move on to the next steps of calculation, where we know that sigma z, that is normal stress, sometimes of course called the direct stress, is given as mx by Ixx into y. Now, let us try to find out Ixx for the given cross section. So, if we start from this, so if we start from this point and try to find out, so from this point O, and let us start the angle from here. So, let this be the angle theta that we consider. If this is the angle theta, theta is going to vary from 0 to pi. If this is the angle theta, then distance of any small element from the x axis y, that is y, is going to be given as r plus r cos theta. So, it is always going to be r plus r cos theta. So, sorry, this was this is the angle that we are talking about. Which is theta. So, the y distance of a small element is always going to be r plus r cos theta, that is this distance. So, if this is the y distance, then we can say that Ixx, which is area integral of y square dA, can actually be written as r plus r cos theta, which is the y distance, that is whole square, into dA can be written as r d theta. R d theta is the elemental circumferential distance into the thickness. So, this whole constitute the elemental area dA. Now that we have written the expression in terms of theta, theta is going to vary from 0 to pi, and then I have to multiply by a factor 2 because to consider the symmetric portion in the bottom side of the x axis. So, if this is the integral that we are trying to find out, so this can actually be written as 2 r cube into t So, the entire integral boils down to finding out this. So, if we expand this, this is going to be 2 r cube t 0 to pi 1 plus 2 cos theta plus cos square theta into d theta. So, if we evaluate this integral, so this can actually be written as 2 r cube t, then integral of 1 will be theta, and then 2 cos theta would be 2 sin theta, and cos square theta, if we integrate that in terms of in terms of cos 2 theta, this is going to give us theta by 2 minus 1/4 into sin 2 theta, and the limits are going to be from 0 to 2 pi. If we evaluate this integral further, this will end up being 2 r cube t pi plus pi by 2, which will be 3 pi r cube t. So, therefore, my Ixx for this two symmetric semicircular cross section is 3 pi r cube t. So, this is the expression 3 that we will be using. Now, once I have got Ixx, then my sigma z can be normal stress or direct stress sigma z can be written as mx by Ixx into y. So, mx is going to be 3500, and if we substitute the value of r and t, we get this as 3 pi. R cube is going to be 5 into 10 to the power minus 3 meter whole cube into 3 is 0.64 into 10 to the power minus 3 into multiplied by y. So, if we calculate this further, then this is going to be 3500 y into 3 pi into 25 into 0.064 into 10 to the power minus 12. Then this is the expression of Newton per meter square. So, this is the expression that we have. Now, let us investigate where are we going to get sigma z max. So, it is very easy to evaluate sigma z max in this particular case, because it is only varying in y. So, we do not have the x coordinate appearing in this equation. So, the maximum value of y is going to give us the maximum value of sigma z. So, if we say that y, this is going to happen at y equals to y max, which is going to be 2r. Okay. So, if we plus minus 2r. So, either the maximum tensile normal stress or the maximum compressive stress. So, if we put 2r, then this is going to be 3500 into 2 into 5 into 10 to the power minus 3 by 3 pi into 25 into 0.64 into 10 to the power minus 12 Newton per meter square. Now, if we calculate this further, we can figure out that sigma z max is going to be 46.4 GP. So, this is the answer that we are looking forward to. So, this is the answer of the problem to find out the maximum normal stress or direct stress in the cross section. So, next we will try to find out, derive what would be the expression of deformation when a beam is under bidirectional bending. So, let us consider any arbitrary cross section. Let this be the x and y axis, which is the cross sectional plane of the beam. So, this is, we are going to draw the cross section of the beam. So, let us take any arbitrary cross section. Let us take any arbitrary cross section. Let me draw the neutral axis. We know that the neutral axis is going to pass through the centroid. So, this is going to pass through the centroid. So, this is the centroid C, and the neutral axis passes through the centroid and it is tilted to the centroid at an angle alpha. The alpha will depend on the moments that are applied to the cross section as well as the sectional properties of the cross section. So, we have found out how to obtain the value of alpha in the earlier lectures. Now, if this is the cross section, so this is the, let me call it Ci, to denote that this is the original or initial position of the centroid of the cross section before bending. Now, if we apply the bidirectional bending, so if we apply the bidirectional bending, let the cross section be deformed. So, let this be the deformed or deflected cross section after the bending has been applied. So, if this is the deflected thing, so let us mark the new position of the centroid as C final, and let the perpendicular distance of this be xi. Okay. So, what is happening? The dotted line is the deformed or deflected shape, deflected cross section. Okay. So, now we have that the cross section CI is the initial position of the centroid. Now, CF is the final position of the centroid. After deflection. Now, this is the perpendicular distance of CF Okay. So, let us try to understand the problem. So, this problem, so we are still using Euler-Bernoulli beam theory as we have mentioned in the last lectures. Okay. So, let us try to understand how it is similar to unidirectional bending of beams. So, in unidirectional bending of beam, when the beam gets deflected, okay, then the centroid of the cross section gets deflected by a distance w. So, this w is also the perpendicular distance of the initial position of the centroid and the final position of the centroid in a perpendicular direction to the neutral axis. So, when the beam is bending under bidirectional movement, then the similar thing is happening. The CI, which was initial position of the centroid, will move to a new position CF in a direction perpendicular to the neutral axis. So, let me reiterate. So, the centroid will due to the deflection, the centroid will move to a new position and this position will be in a perpendicular direction to the neutral axis. So, CF is the new position of the centroid, we have assumed that. Now, and Z is the perpendicular distance between the perpendicular distance of the new position CF from the neutral axis. So, in unidirectional case, the neutral axis was horizontal, which was parallel to the x axis. Now, the neutral axis for the bidirectional case is tilted to the x axis, but even in this case the movement of the centroid will be perpendicular to the neutral axis. So, this is going to be perpendicular to the neutral axis, similar to the unidirectional bending case. Now, zeta is the distance of CF in the perpendicular direction from the neutral axis. Then, from Euler-Bernoulli beam theory, I can say that the 1 by the radius of curvature can be written as 2 into pi 2 del z square. Okay. So, this z is this g is the perpendicular distance from the neutral axis and r is the radius of curvature. So, this is given by the Euler-Bernoulli beam theory. So, now again we can see from geometry, let me draw this, we can see from geometry that the distance z can be resolved in x and y direction, and the x deformation we can call it as u and the y deformation we can call it as v. So, if this is the angle alpha, then we can say that u is nothing but minus z into sin alpha, and v is nothing but minus z into cos alpha. If this is the angle alpha, if you carefully look, then you can see that u is just sin alpha. So, this angle will also be alpha, and therefore, u can be written as minus g sin alpha and v can be written as minus z cos alpha. Now, we can say that therefore, del 2 u by, so from this expression we can say that del 2 u by del z square can be written as sin alpha by r, because del 2 u by del z square is going to be d 2 z by dz square into sin alpha. Similarly, minus del 2 v by del z square can be written as cos alpha by r, which is basically d 2 z by dz square into cos alpha. Now, if these two expressions are obtained, then we can say that 1 by r sin alpha and cos alpha can actually be written as minus d 2 u by dz square and minus d 2 v by dz square. So, this can be written in simplified notation as u double dash and v double dash. Now, from our previous calculations, we have seen that 1 by r sin alpha cos alpha can further be written as 1 by e into minus ixy ixx by, or let me erase this off and write it in a better way. So, we can say that we have seen from our previous expression that sin alpha and cos alpha can actually be written as 1 by this expression we have derived earlier. Now, from this expression we are again 1 by r sin alpha cos alpha is related in this way. So, this can therefore be written as u double dash v double dash is minus 1 by e Now, if we inverse this relation, then we can write mx and my in terms of u double dash and v double dash as minus e ixy, ixx, iyy, ixy into u double dash and v double dash. This can be written in a simplified way as mx is minus e ixy into u double dash minus e Now, this two equation can be used to solve for u double dash and v double dash, which are the deflection of the beam in x and y direction due to the bending moment mx and my. So, we will solve certain examples on this in the next lecture. Thank you.